The deep dive. Today we're tackling something pretty common. Actually, trying to hear just one person talking when there's a ton of background noise.
Yeah, that noisy cafe problem or the office chatter.
Exactly. And for technology, trying to isolate one specific voice from all that sound, that's a massive challenge. It's called target speaker extraction, or TSE.
Right. And it's super important for, making communication better, improving hearing aids, even making voice assistants work when it's loud.
So TSE, we should probably define that a bit more clearly.
Good idea. So TSE is technically about isolating the speech of a specific target person from a mixture of sounds, other voices, noise, music, whatever.
And you need to know who you're listening for, right?
Exactly. You usually give the system a little sample of their voice first. That's the enrollment audio. That's key.
Okay, so it's not just general noise reduction.
No, that's speech enhancement, SE. That just tries to clean up all speech. TSE is specifically targeting one known speaker. Getting it right means, well, clearer calls, much better hearing aids, ASR that actually works in a crowd.
And we're looking at a specific paper today, right, about a new approach.
Yep, a paper introducing something called FlowTSE. Our mission basically is to unpack it, figure out what FlowTSE is, how it works, and crucially, what's new about it. What's the innovation here?
Great. So let's start with the core problem TSE faces.
Okay, so imagine that party scenario again. You're trying to follow one friend's story. The system has to pick out their voice from everyone else talking, music playing, background clatter. It's tough.
And how have people tried to solve this before? You mentioned different types of models.
Right. Broadly speaking, there are two main strategies: discriminative models and generative models.
Okay, discriminative. Those are the ones that sort of learn a direct filter from noisy to clean.
Yeah, that's a good way to put it. They learn a direct mapping, go from the messy input mix straight to the estimated clean speech, and they can work pretty well.
But downsides.
Sometimes. It can sometimes introduce weird sounds, artifacts, or maybe not generalize perfectly to completely new kinds of noise or speakers they haven't been trained on extensively.
And generative models, they work differently.
Totally different philosophy. Generative models try to learn the underlying structure or distribution of clean speech itself, conditioned on who the speaker is. The idea is they can often generate higher fidelity, more natural sounding results.
Okay, so generative sounds promising, but the paper mentioned some issues.
Exactly. The authors point out that while generative are getting good results, they're still underexplored. And the quote they use is key. Most existing approaches relying on complex pipelines and pre-trained components, leading to computational overhead.
So they're often complicated. Sticking things together, needing big pre-trained models.
Precisely. That complexity, that reliance on other big models, the computational costs, that's the gap FlowTSE is trying to fill.
So FlowTSE comes in claiming to be generative, but simpler. That sounds like the goal.
That's the core pitch, a simple yet effective generative approach. And the key technology they use is flow matching, specifically conditional flow matching, or CFM.
Flow matching. Okay, what is that exactly? Not diffusion, you said?
Right. It's related to diffusion models, but different. Instead of learning gradients, flow matching learns like a smooth path or floor. Think of it as learning how to continuously transform a simple distribution, like noise, into the complex distribution of your target data, in this case, the clean speech spectrogram.
So it learns the velocity needed to move from noise to the clean signal.
That's the intuition. It learns a time-dependent velocity field, the direction and speed to follow at each step along this path. And the conditional flow matching objective they use, it actually simplifies the training quite a bit.
How so?
It basically trains the model to predict the velocity needed to go from any point along that path directly towards the final target, the clean speech. Equation 1 in the paper shows this simplified form xt equals 1-x0 plus t. It makes calculating the training loss more straightforward.
Okay, makes sense conceptually. How is the model actually built? The architecture, you mentioned it takes the enrollment and the mixed audio.
Right. It works with mel-spectrograms, which are these time-frequency representations of the audio. They're computationally efficient. It takes the mel-spectrogram of the enrollment speaker and the mel-spectrogram of the mixed speech, concatenates them, and feeds them in.
Mel-spectrograms are efficient, but you hinted at a catch.
Yes, we'll get back to that. It's important. The architecture itself uses building blocks common in sequence modeling, like diffusion transformer blocks, adapted for this flow matching process. They use things like adaptive layer normalization to handle the time aspect of the flow.
And how does it use the speaker's voice sample?
Crucially, the parts of the model processing the mixed audio are allowed to attend to or look at the parts processing the enrollment audio. That's how it incorporates the target speaker's unique vocal characteristics to guide the separation. The final output is the predicted clean mel-spectrogram for the target speaker.
And then inference? getting the actual sound back?
Yeah, during inference, you start with noise, basically a random mel-spectrogram, and you use the learned velocity field with an ODE solver, a numerical method to integrate along that path, step by step, until you arrive at the estimated clean mel-spectrogram.
Okay, now back to that catch with mel-spectrograms. The phase information. Why does losing that matter so much?
It's a really good question. For a lot of things, like just basic speech recognition, maybe it's okay. Standard vocoders can often estimate phase reasonably well.
But not always.
Not for everything. If you need really precise timing, or if the output needs to feed into another system that works directly on the audio waveform, like say Hubert, then phase becomes critical. Or for really high fidelity uses, think professional audio or advanced hearing aids doing complex spatial processing. Without accurate phase, the waveform might sound okay spectrally, but have subtle timing issues or artifacts.
And the paper calls this out?
Explicitly, they state, one key challenge for generative-based TSE approaches utilizing MEL-based vocoders is the lack of explicit phase modeling, as MEL-spectrograms do not retain phase information.
So FlowTSE uses mel-spectrograms for its core simplicity, but needed a fix for the phase issue.
Exactly. And their solution is pretty neat. The phase-conditioned vocoder. It's not a brand new vocoder from scratch, but clever modifications to an existing one, like vocos.
Okay, what are the modifications? How does it bring phase back?
Two key things. First, inside the vocoder architecture, they add cross-attention layers. These layers let the vocoder, while processing the generated mel-spectrogram, also look at features from the original mixed speeches complex STFT.
Ah, the STFT still has the phase.
Precisely. The short-time Fourier transform retains both magnitude and phase, so the vocoder gets access to that lost timing information from the original mix. Second, they modify the final stage, the inverse STFT part that actually reconstructs the waveform.
How?
They make it learnable in a specific way. It predicts complex coefficients, essentially learning how to combine the phase it predicts with the actual phase from the mixed signal. It's like a weighted combination. SISM plus ESP, where SIM is the mixed signal STFT and SPIV is the predicted one. It uses the mix's phase as a guide.
That is clever. Use the main model for the what's spectral content and the vocoder plus original mix for the when phase timing. Did it work? How did this phase vocoder do in tests?
Well, this is where it gets really interesting. They tested it, and yes, it significantly improved the SI-SDR score. SI-SDR, signal-to-distortion ratio, is very sensitive to waveform accuracy, including phase and timing. So mission accomplished on that front.
But, I sense a but.
There's a trade-off. The paper notes this improvement may come at the cost of lower scores in other metrics, such as p-skew, STOI, and OVRL.
Oh. So better technical phase accuracy didn't mean better perceived quality according to those other standard metrics.
Exactly. PSQ, STOI, OVRL. These are designed to correlate better with how humans actually perceive speech quality and intelligibility. So improving the phase accuracy technically didn't necessarily make it sound better or clearer to a listener by those measures. It's a fascinating trade-off.
Wow, okay, that's a really important nuance. So let's put the vocoder detail aside for a second. How did FlowTSE, the whole system, stack up against other TSE methods overall?
They ran extensive tests on the standard Liber2 mix dataset using various conditions like mixtures with noise, other speakers, or both. And they used a range of metrics.
PSQ, STOI, those perceptual ones, and speaker similarity.
Yes, PSQ, STOI, OVRL, DNSMOLs for quality and perception. SIM for speaker similarity, does the output sound like the target? And also WER for intelligibility, plus SI-SDR, which we just discussed.
And the results?
Very strong. In the main results table, FlowTSE got the highest PEQ score overall. In some settings, it even beat the original clean speech baseline on metrics like OVRL and DNSMOS, which is quite something. It also got good SIM scores, meaning the speaker identity was preserved.
So it sounds good and sounds like the right person.
Pretty much. The authors summarize it well. Our results demonstrate that FlowTSE achieves performance matches or outperforms strong baselines while maintaining a simpler and more efficient pipeline. Performance plus simplicity.
What about understanding the words? The intelligibility, WER.
Right, crucial point. They tested WER on a specific Liber2 mix split. FlowTSE achieved a much lower word error rate than a tumpable model, WhisperTSE, and was very close to a much, much larger model, WhisperTSE.
Even though those whisper models were specifically trained using ASR data to minimize WER.
Exactly. FlowTSE wasn't explicitly trained with an ASR loss, but its generative approach seems to inherently produce highly intelligible speech. That's a significant plus.
And you mentioned it could even do basic speech enhancement.
Yeah, as a bonus test, they applied the same TSE trained model to a simpler task, just one speaker mixed with noise. And it did really well, even getting top scores on PCSQ and OBRL in that setting too. Shows the model learned something fundamental about clean speech.
So stepping back, what's the bigger picture here? Where does FlowTSE fit in?
Well, it's a solid contribution from the researchers at Yael, Aviv, Navon, Aviv, Shamsian, and others. It plugs into this broader effort across many labs exploring generative models, flow matching, diffusion, etc. for audio. FlowTSE really makes a case that these newer generative techniques, especially flow matching, can offer a simpler yet powerful alternative for tough problems like TSE.
Okay, so summing it all up, what does this mean for us, for the listener?
I think it shows a promising direction. FlowTSE suggests we can potentially build highly effective voice separation systems that are less complex, computationally cheaper, and maybe easier to train than some of the current state-of-the-art methods that rely on very large models or intricate pipelines.
The use of flow matching on mel-spectrograms seems key to that simplicity.
Absolutely. And the phase-conditioned vocoder, even with its trade-offs, is a great example of the clever engineering needed to overcome the limitations of certain approaches. It shows researchers are thinking hard about how to get the best of both worlds, efficiency from mel-specs, accuracy from careful phase handling. As they say, we believe that FlowTSE drives TSE toward more simplified and effective generative approaches.
Right, so just to recap the highlights, FlowTSE uses this flow matching technique for a simpler generative pipeline on mel-spectrograms to separate voices. And then there's that very clever phase-conditioned vocoder to handle the phase issue, albeit with some interesting evaluation trade-offs.
Exactly. And for you listening, seeing how FlowTSE works gives a window into how researchers are tackling these really complex audio challenges. It's about balancing efficiency, simplicity, and performance. That whole phase vocoder discussion showing how improving one technical metric like SDI, SDR doesn't automatically improve perceptual ones like PESQ. That highlights the real-world complexity of evaluating what better actually means for different applications.
It's not always straightforward.
Definitely not. And that brings up a final thought, building on that vocoder trade-off. Where does generative audio go from here? Will future systems prioritize technical waveform accuracy, chasing metrics like SASDR, which might be vital for certain system integrations? Or will the focus be more on perceptual quality and intelligibility, metrics like PSQ or WER, which reflect the human experience more directly?
So will the benchmark themselves evolve depending on the end goal?
It seems likely, right? Different applications like hearing aids versus transcription services versus music production might weigh these different aspects of quality very differently. It'll be interesting to see how the field balances those competing priorities.
A really interesting question to ponder. Thanks for unpacking FlowTSE with us today.
My pleasure.